Case 2 is E less than V of x, which is classically forbidden region. Classically forbidden region. Here, P of x is imaginary and the exponents are real, and the wave function psi of x is given by psi of x equal to c minus bar root of mod P of x exponential minus I by h cut integral lower limit x mod P of x bar dx bar plus c plus bar by root of mod P of x exponential 1 by h cut integral upper limit x P of x mod P of x bar dx bar. And the third case is the point E equal to V of x. Energy and potential are equal. These are called classical turning points. Here, the classical momentum P of x is equal to 0. Particle stops at these turning points and turn back to move in the opposite direction. Since classical momentum at this point, turning points P of xi equal to 0, the wave function is also 0. Psi is also 0 at these points. Next is validity of the WKB approximation. How far is it valid? Consider the term a del s o square and I h cut a del square s in the equation 8. They are very small since the quantities of order h cut are too small in the classical limit. The quasi-classical region expected is given by the following condition. Substitute psi of r equal to e raised to I s of r by h cut in equation 2. In equation 2, that is del square psi of r plus 1 by h cut o square p square of r psi of r is equal to 0. And multiply the equation by h cut o square. Then we get to the equation I h cut del square s of r minus del s o square plus p square r is equal to 0. In the classical limit, the term containing h cut, that is I h cut del square s of r, must be very small compared to the terms that do not have, that is del s o square. Therefore, mod h cut del square s is very much less than del s o square. In one dimension, h cut mod s double dash by s dash square is very much less than 1. That is modulus of d by dx of h cut by s dash very much less than 1. We know s dash or ds by dx is equal to plus or minus p of x. Substituting this, we get modulus of d by dx of h cut by p of x very much less than 1, or modulus of d by dx of lambda bar x is very less than 1, where lambda bar of x equal to lambda of x by 2 pi, or lambda bar of x is equal to h cut by p of x, or h cut by root of 2m into e minus v of x. Here, equation 19 is the condition of validity of WKB method. Equation 18 shows that rate of change of de Broglie wavelength is very small. When p of x is too small, classical momentum is too small, lambda bar becomes very large according to the above equation. And the validity condition for WKB and it violates the validity condition for WKB. WKB approximation is valid both in the allowed and forbidden regions, that is E less than V of x at E less than V of x and E greater than V of x. But at the classical turning point E equal to V of x, since the classical moment of V of x becomes 0, psi of x is iso-zero and WKB is approximation is not valid at the turning points. Now consider a particle moving in the potential well. Here x1 and x2 are the turning point. We have made an approximation that the potential to be given near the turning points x1 x2 is given by a straight line whose slope is equal to the potential at that point. The energy level formula depend upon whether or not potential well has rigid walls and their number. We consider potential well with no rigid walls. Here x less than x1 and x greater than x2 are the forbidden region, and that is region 1 and 3. x1 less than x2 is the allowed region. By the WKB approximation, using the WKB approximation, we can find the equation for the wave function psi plus or minus of x equal to c plus or minus by root p of x exponential plus or minus I by h cut integral x p of x prime dx prime. Using this, we can find the equation for the wave function at three regions, those three regions. Using this, psi 1 of WKB, the wave function in the first region, is given by c1 by root of mod p of x exponential minus 1 by h cut integral x to x1 mod p of x prime dx prime in the region x less than x1. Psi 2 of WKB equal to C2 bar by root of px exponential I by h cut integral x p of x prime dx prime plus C2 double bar by root of px into minus I by h cut integral x p of x prime dx prime in the region x1 less than x2. Psi 3 of WKB equal to C3 by root of mod p of x exponential minus 1 by h cut integral x2 to x mod p of x prime dx prime in the region x greater than x2. Here C1, C2 bar, C2 double dash, C3, C1, C2 dash, C2 double dash, C3 are coefficients. They can be found out by connecting the solutions psi 1 of x, psi 2 of x and psi 3 of x when passing from one region to other through the turning points x1 and x2, where WKB is not valid. They are connection equations. At these turning points, we have to find an exact solution of the Schrodinger equation near x1 and near the turning points x1